In this video, we are going to begin to talk about how we find eigenvalues and eigenvectors of a 2 by 2 matrix, a matrix with 2 rows and 2 columns. I'm not going to go into any of the theory of why these procedures work. If you're interested in the theory, I recommend taking linear algebra. I'm just going to quickly go through the basic process, and we're going to get some practice using that process so that we can turn around as quickly as possible and go back to our setting of systems of differential equations and trying to solve those. If you have a matrix A, if you want to find its eigenvalues, you can use the following procedure. The first thing that you want to do is subtract an unknown number. Let's just call it lambda, that's traditional, from both of the entries on the main diagonal. Then you want to take the determinant of the result and once you've found that determinant, set the result equal to 0 and solve for lambda. The solutions will be the eigenvalues of the matrix. To demonstrate this technique, let's consider this matrix -1, 1, and 4, -1 that we worked with in the previous video. We have already seen that this matrix has at least 2 eigenvalues. We saw, for example, that there is an eigenvalue equal to -3. We were able to multiply a vector by this matrix, and the result was -3 times what we started with. In the previous video, we also saw that the number 1 was an eigenvalue. There was a special vector out there so that when we multiplied that vector by this matrix A, the result was 1 times what we started with. Now let's see how the procedure described above can give us another way to find these particular values. I'm going to start by going into this matrix, and for each of the entries on the diagonal, I'm going to subtract this variable called lambda. So now I have the matrix -1 minus lambda in the top left entry. I'm not changing the entries off the diagonal at all. And then I have -1 minus lambda, subtracting lambda from the second entry on the diagonal. Okay. Next, I was asked to find the determinant of this matrix. So using the traditional formula for the determinant of a 2 by 2 matrix, I'm going to find the determinant of this matrix written here. So that would be equal to the product of the 2 entries on the main diagonal minus the product of the 2 entries on the off diagonal, giving me 1 plus 2 lambda plus lambda squared minus 4, giving me lambda squared plus 2 lambda minus 3. Next step in the procedure, they tell me set this result equal to 0 and solve that for the values of lambda. So I'm going to take lambda squared plus 2 times lambda minus 3. I'm going to set that equal to 0, and now I'm going to solve for lambda. So I get lambda plus 3 times lambda minus 1, solving by factoring. And from that, I can deduce that lambda must be -3 or lambda must be 1. And these two numbers, these two solutions, these two lambda values coincide exactly with the eigenvalues that we saw in the previous problem. So this technique can be used to find the eigenvalues of a 2x2 matrix. For another exercise, to reinforce the process, let's consider the following matrix A, 10 minus 9, 4 minus 2. Let's try and find the eigenvalues of this matrix. So I'm going to go into the matrix, and I'm going to take the entries on the diagonal, and I'm going to subtract this unknown lambda. I'm going to leave the other entries alone. Then I'm going to take the determinant of that quantity. So I get 10 minus lambda times minus 2 minus lambda. Take away negative 36. Now if I expand that, I get lambda squared. It looks like plus 2 times lambda, negative 10 times lambda, negative 20. So it looks like lambda squared, it looks like negative 8 lambda, and it looks like plus 16. Now if I set that quantity equal to 0, and I solve for the lambda value, then I find that we only have one eigenvalue here. Lambda is equal to 4. And for final demonstration, for a final exercise showing the process, let's find the eigenvalues of this matrix. For minus 2, negative 7, 1, 2, I start by subtracting lambda from the diagonal. Then I find the determinant of the result. So I get 2 minus lambda times minus 2 minus lambda. Take away the product on the off diagonal. I simplify, giving me lambda squared plus 2 times lambda minus 2 times lambda, and then minus 4. Then plus 7 in the back. And if I simplify that and set it equal to 0, I find that I have actually complex eigenvalues. Plus minus the square root of 3 times I from lambda squared equals minus 3. Now that we've learned how to manually find the eigenvalues of a matrix, we can talk about how to find the eigenvectors of a matrix. Now, to find an eigenvector corresponding to a specific eigenvalue, we can use the following procedure. We go back into the matrix and we subtract the eigenvector from the diagonal entries. Then we're going to look for a non-zero vector, let's call it V, so that multiplying by the matrix above gives us a 0, 0 as a result. Let me demonstrate to you what I mean with an example. Let's return for a moment to this matrix negative 1, 1, 4, negative 1. In yesterday's video, we showed that this matrix had eigenvalues negative 3 and 1. the eigenvalue, -3, corresponded to the eigenvector 1, minus 2. Similarly, we found that the eigenvalue of 1 had a corresponding eigenvector of 1, 2. Now let's see if we can get these results using the procedure written in blue above. So to find the eigenvector corresponding to -3, the procedure suggests that I start by subtracting -3 from the diagonal entries. So in the matrix A, I'm going to take -1 minus -3 and subtract it from the diagonal entries. So -1 plus 3 is 2, then 1 and 4, and then 2. Okay, now the procedure is asking me to try and find a vector v1, v2, so that when I multiply this matrix by this vector in green, the result is equal to 0, 0. Any vector v1, v2 that satisfies this equation will be an eigenvector corresponding to -3. Now, do you recognize this situation from yesterday's video? We're in a situation where the matrix on the left-hand side, the bottom row is just a scaled version of the top row. So even though there are technically two equations that need to be satisfied, the top product must equal 0, and the bottom product must equal 0. Equation number 2 is redundant. Equation number 2 is just a doubled up copy of equation number 1. So equation 1 is the only one that really is worth caring about, and a simple choice of v1 and v2 that makes this equation true is just to pick v1 equals 1 and make v2 change to -2 to compensate. And so we get the vector 1, -2, which just so happens to be the eigenvector corresponding to the -3 that we're working with now. Let's try the same thing with the other eigenvalue, lambda equals 1. I'm going to go into the matrix A, and I'm going to subtract 1 from the entries on the diagonal. So -1 minus 1. Now simplifying gives -2, 1, and 4, -2. And I'm in search of a vector which, when multiplied by this modified matrix, gives me 0, 0 as a result. But once again, notice that the second row in this matrix is just a scaled up version of the first row in this matrix. The second row is just -2 times the first. So although there are technically two equations that must be equal to 0 here, only one of them really matters, because the second one is just a scaled version of the first. So all I have to do is find v1s and v2s that make this first equation true. And a really easy choice, again, is just to make v1 equal 1 and v2 change to 2 to compensate. So from that, I find an eigenvector 1, 2 to accompany the eigenvalue of lambda equals 1, which exactly matches what we found yesterday during our exploration. So this procedure can be used to find the eigenvalues and eigenvectors of a matrix. You start by finding the eigenvalues by using the determinant process described in Part 1. Then for each of those eigenvalues, you subtract them from the diagonal, and then you go in search of a vector so that that vector multiplied by the modified matrix equals 0. Let's try it one more time all together on the matrix 3, 1, 1, 3. Let's find the eigenvalues first, and then let's find the eigenvectors that correspond to those eigenvalues. Starting first with the eigenvalues, I'm going to go into the matrix. I'm going to subtract an unknown lambda from the diagonal entries, and I'm going to find the determinant. So I have 3 minus lambda squared, take away 1. I get lambda squared minus 6 lambda plus 9 minus 1, lambda squared minus 6 lambda plus 8. Then I set that equal to 0, and I solve for lambda. Here I can solve by factoring. And so I get 2 eigenvalues. One is equal to 2, and the other is equal to 4. Now let's find the eigenvectors corresponding to these eigenvalues. Starting, for example, with lambda equals 2. When lambda is equal to 2, and I subtract 2 from the entries on the diagonal, then 3 minus lambda becomes 3 minus 2, becomes 1. I then look for a matrix. I then look for a vector v1, v2, which, when multiplied by this matrix, gives me 0, 0. But again, because the second row of the matrix is a scalar multiple of the first, there's only one equation that I really have to be concerned about. 1 times v1 plus 1 times v2 equals 0, which can be easily solved by setting v1 equals to 1 and forcing v2 to change to compensate. So an eigenvector corresponding to lambda equals 2 is given by 1 comma minus 1. Similarly, if I wanted to find the eigenvector corresponding to the other eigenvalue of 4, then I go into the matrix A, and I take 4 away from all the entries on the diagonal. So 3 minus 4 I'm looking at negative 1, 1, 1, negative 1. I'm looking for a vector, which when multiplied by this matrix gives me 0. Because the bottom row is redundant of the first one, all I really care about is row number 1. And this equation can be solved by setting v1 equal to 1 and forcing v2 to compensate. So the eigenvector corresponding to the eigenvalue of 4 is 1 comma 1. Now that's the basics of how we calculate eigenvectors and eigenvalues of matrices. Tomorrow, what we're going to do is we're going to talk about what happens in the case that we have complex eigenvalues, as we saw at the very beginning of this problem. And then in the next 2 days, we're going to talk about how to use eigenvalues and eigenvectors to solve systems of differential equations.